Welcome back to our series on multivariable calculus. In this episode, we're going to talk about drawing parametric vector space curves that represent surfaces. We've already looked at parametric equations, parametric vector curves, earlier in the semester. And of course, those were in the form of R of t, where we had an x component, y of t, y component, and z of t, z component, and we use these in order to draw curves in space. It was convenient because it just reduced it down to a single parameter that drew the whole curve and represented three variables with one variable. It also opened the door for all of the vector functions, to vector dot products and cross products, which we've found are really powerful in analyzing a lot of things we're interested in multivariable calculus. Well, we want to do the same thing except for these two-dimensional functions. So when we have z as a function of x and y, of course it maps out a surface, and we can't use a single variable parametric to do that. Recall that what R of t did was went from the origin to a point in space, and then as t changed, it sort of swung around and drew the curve for us. But it was limited to things that were of infinite thinness and whatever length we wanted. In this case, we want to draw a surface, so we need to extend our parametric function in order to draw in two dimensions instead of one. And of course, for that, we need a two-dimensional vector curve. So we're going to introduce a new idea, which is R of u and v. These are parameters like t, and it will give me an x of u and v, a y component of u and v, and a z component of u and v. So it will act very much like our existing parametric curve. That is, this r will point from the origin to a point in space, but now I have 2 degrees of freedom, which means that I can draw along in one direction and then I can move perpendicular to that and continue to draw. Basically, I can track out lines in space that are very close to each other, therefore mapping out an entire surface. So that's how it works. It turns out that almost every f of x and y we've looked at can be parameterized in this way. And that way it's going to open up to surfaces our ability to apply our very powerful vector functions of dot products and cross products, partial derivatives and all of that. Okay, well, let's take a look at how we might do that for a typical function. So let's look at something easy. Let's look at f of xy is equal to ax plus by. So this would in essence represent some sort of a planar surface. In this case, f of xy represents the z, so it would be z equals ax plus by. Because f of xy can be so easily written in terms of x and y, that is, we can explicitly solve for the z variable, it opens up the door to a really easy shortcut, which is r of u and v, which might model this guy right here. I would simply use u for x, v for y, and then I would use the z component or the z coordinate f of xy, that is ax plus by, but because I've already decided that x and y are going to be represented by u and v, this would be au plus bv. And there it is. With the appropriate choice of u and v, just those two parameters, I can remap out this entire surface. Now in this case, you might wonder, what's the advantage of that? I replace the variables x and y with the variables u and v. But this is a vector function, which means we can do things with it that we couldn't do with a conventional function. These had no directions to them. They didn't point anywhere. These do, and there's some really powerful ramifications of the variables u and v that will allow us in essence to utilize u and v to redefine our coordinate system in ways that's going to really benefit us. Okay, so this becomes kind of our first rule, which is as a shortcut, you can almost always parameterize any function u and v just by assigning u to x, v to y, and f of uv to its z coordinate. Now, of course, to do this, you have to be able to list the function explicitly as a function of z equals. If you can't do that, then this turns out to be really difficult to do or often impractical. And sometimes the function definition is really complex. It contains square roots and higher powers and internal products, such that applying our vector functions to the parameterized equation might prove problematic. Remember, we're going to want to be able to do dot products, cross products, partial derivatives of this, which means this third term, it's nice if it's easily differentiable, if it's easy to integrate and apply vector functions to. Okay, let's look at a second example, one that's a little bit more relevant because it's a curve that can't really easily be expressed as a function of z. And that, of course, is a sphere. A sphere would be x squared plus y squared plus z squared equals a squared, where a represents the radius of the sphere. This would be a sphere in standard position. Well, what we can do is take our clue from polar coordinates. I could just go with the shortcut, and just for the sake of argument, let's look at what that would look like. By the way, this is not a good choice. So I could parameterize it by RUV being equal to U, V, and then look at how awful the z component needs to be. First of all, there's two of them, plus or minus. So these both can't possibly be represented by the same vector function. I would need r for the upper half and r for the lower half. But this is what it would look like. It'd be the square root of a squared minus x squared minus y squared. Can you imagine taking partial derivatives in terms of u and v? And again, that x and y here, this should really be u for x and v for y, because once again, we're writing it as a parametric equation. Again, not a good choice. While it's practical, and this is a parameterized version of the sphere, and it will map out the sphere if I plug in values for u and v, it's not practical for our purposes. Let's think of another way we could write this then. And again, this I'm going to borrow from the idea of polar coordinates. As a matter of fact, I'm actually going to write it in the polar coordinate variables, because there's nothing magical about the variables u and v. We will use them frequently for parameters, but there's nothing magical about it. We're not locked into using them exclusively. And when I want to represent a sphere, it actually makes sense to use theta and phi, because those are the variables that we're used to. Okay, I can also map this out by mapping out the x, y, and z components utilizing our conversions for spherical coordinates. That is, the x component is going to be whatever the radius is, and in this case that's a, times the sine of phi times the cosine of theta. And then the y component is going to be a times the sine of phi times the sine of theta. And then the z component is going to be a times the cosine of phi. And there it is. These values of theta and phi become the two parameters that, as I select them using the constant a value, this will map out every point on the surface of that sphere. And you notice that while these are relatively complex terms, they're easily differentiable in terms of partial derivatives. I could do dot products and cross products. And we know what happens with these. Once we find magnitudes, a lot of it simplifies out, so the integrals with them turn out to be simple. Let me introduce one final concept, and that's the idea of drawing something by moving vertically through it. This works particularly well for things that have circular symmetry in the xy plane, like a sphere. So let's parameterize this a second way. I'm going to use u and v for this one. And the idea here is I want to move upward through the sphere, drawing concentric circles that stack on top of each other, that get larger in radius and then smaller in radius, and they map out the whole sphere. Well, to do that, I need circles of variable radius. So that's going to be cosine of u and sine of u for the x and the y components. In the z direction, I'm just going to use v, and v will be the altitude I move to that controls that radius. Well, here's the deal. How do I control that radius? If I want the sphere to be of radius a, here's the coefficients. It'll be a squared minus v squared under the radical, a squared minus v squared under the radical. What these will do is guarantee that the circles begin when I'm at the lowest point when v equals negative a. This will be 0, so I'll be at that dot at the bottom of the sphere. And then as I start to move upward in terms of v, this differential will get smaller and smaller so that the radius gets larger and larger, and I'll start to draw circles that are larger. Once I reach where v equals 0, I'll actually draw a circle of radius a right in the xy plane. And then it'll flip around and they'll get smaller and smaller once again up to the point where v equals a, and we're at the top point, and then of course the radius will go back to 0. This set of parametrics is very powerful. You'll notice it does have the disadvantage that the partial in terms of v will be a little bit messy. But it has the advantage that it's defined vertically, which means it has a very easy z component. Either one of these are appropriate parametric choices for drawing a sphere. You can choose one or the other based on what your application is. And that's the central lesson here, is that there isn't one way to parameterize a surface. There's generally multiple ways, and any of them are equivalent to any of the others you choose. How do you know if your parameterization is correct? Well, the bottom line is you simply substitute your x, y, and z component into the original formula you're supposedly modeling, and it must make it true. You'll notice that if we substitute these in, this will make a true statement, which means the parameterization is valid. Any valid parameterization is as good as any other. Okay, it leads to the question of what are we going to do with these parameterizations? What's the value of converting surfaces into vector functions? Well, the whole remaining portion of the course is exclusively devoted to integrals based on these surfaces. We'll be revisiting some of our old friends like Green's theorem. But one of the first applications, of course, is finding surface area. Now, before, when we looked for surface area of a regular old function, we took a double integral of 1 plus fx squared plus fy squared under the radical dA. And this, in essence, is how we found the surface area for a function in this form. We first had to find the two partials, square them, add them to 1. And remember, this entire thing came from the idea that we were actually treating points on the surface as the intersection of two perpendicular vectors that defined a little parallelogram. That parallelogram's cross product was then equivalent to the area of that small element, and its magnitude would then give me, added up, the area of the surface. That's where this came from. So this is the end result of a vector process. But we had to be sort of ham-fisted about it because this was f of xy, so both of our vectors had to lie in the xy plane. And of course now, we're not going to be limited to surfaces that are exclusively above or below the xy plane. We need to be able to integrate the side of a sphere as well. And that's the advantage of our parametric functions, is that they turn with the surface. So that if I take cross products of the partial derivatives of r, I will always get a normal to the surface no matter what its orientation is. In this case, I only got a normal to the surface when that surface was the xy plane. So that's a huge advantage of parameterization, is it allows me to turn the idea of what horizontal is in any direction I want. So our new surface area then is going to be the same vector function. I'm going to take the double integral, but now it's going to be the magnitude of these two partials. So I want r of u crossed with r of v, and then I'll take the magnitude of that du dv. And in essence, what the two partials will give me is vectors that lie in the surface. And of course, if the two vectors are in the surface but they're not parallel, their cross product will give me the area of that small parallelogram they define. And the magnitude of that will be the area of that small piece. And if I integrate that across the entire surface, I will get the surface area. So our surface area formula comes directly from this parameterization. And you can see I need to do both partial derivatives, a cross product, and then a magnitude. That tells us that parameterizations like this one are just not going to fit the bill because they'll be awkwardly complex when it comes to our first step in applying these parameters. That's why parameterizations like this and this just have so much more power. Remember, always try the brute force method, which is just see if the function itself can be explicitly solved for z, and if this parameterization will be adequate to find the surface area. But if it's based on a round geometry, I'm talking cones, cylinders, and spheres, you're going to find that you'll get an alternative parameterization that will make finding surface area much, much easier. Of course, once we have surface area, we can do a lot with that. Once we define a surface, we'll be able to look at flux and curl, so we'll be able to extend Green's theorem out into higher dimensions. Right now, we can only do Green's theorem in 2 dimensions, but we'll be able to do it in 3 dimensions, looking at curl and divergence through surfaces and flux through surfaces that are defined by these new vector functions. So that's for another day. For now, just get comfortable with this process. It can be arduous and detail-oriented, so mind your P's and Q's.